Let's look at this problem. In triangle ABC, point D divides sides AC so that AD to DC equals 1 to 2. So we have this point, D. So this is 1 and this is 2. That's the ratio, remember. It's not the length of the side. It's the ratio of the two lengths. Okay, let E be the midpoint of segment BD. Okay, E is the midpoint. Therefore, BE equals DE. And let F be the point of intersection of line BC and the line AE. So we connect the segment AE and then extend it so that to intersects BC at a point F. Given that the area of triangle ABC is 360, and the question is, what is the area of triangle EBF? Okay, we want to calculate or derive the area of this small triangle BEF. So in order to do that, we want to do one thing, because we don't know the length or anything about it, right? We know some ratios of the line segments. Therefore, the best way to calculate the area of this small triangle is to build a link between this small triangle and the area of the big triangle ABC. For example, if we know the ratio of their area, then we can certainly derive the area of the smaller triangle. So the key point here is to build a link. We need a link from the triangle BEF to the triangle ABC, right? This is the key point to solve this problem. Then let's see how can we build this link. For example, let's start from something simple. Let's look at this triangle, triangle ABD, right? We certainly know that the area of this triangle equals 1/3 of the area of triangle ABC. How is that? Because if we use this segment AD as base for the smaller triangle ABD, and use the line segment AC as base for the triangle ABC, then they are sharing the same height. That is the distance from point B to the line AC, right? So that's quite straightforward. And we have a couple of other relationships. For example, we also know the area of triangle BDC equals 2/3 of the area of triangle ABC. And that's because of the same reason. We use DC as the base of the triangle BDC. And therefore, these two triangles, is sharing the same height from the point B to the line AC. Good. With that knowledge, we know that in order to calculate or derive the area of triangle BEF, we have to build certain connection between this to this triangle or to that triangle, right? We need some kinds of link. All right, let's start from this one. Let's call this is first, this is second. If we can build a link between either one, then we can solve the problem. For the first one, the hard part is this. Let's look at this triangle ABF, right? So we can use this line segment AF or AE or EF. We can use that as base and use the distance from B to AF as the height of either this triangle or maybe this triangle, BEA, right? But either way, the hard part of that is we don't know how E divides AF. Do we know that? We don't. We know how E divides BD, but we don't know how E divides AF. Therefore, the connection or the link of one of this relationship is unclear. It's not very clear. We can't do much about it unless we know how this E cuts AF. So certainly we fail in here. Then let's look at the link 2 here between these two triangles. In order to do that, maybe we connect this line segment, right? So if we connect that line segment, it's easy to derive that the area of triangle BEF equals a half of the area of triangle BDF, right? That is because E bisects BD. So we can use BE and BD as their base, and they're sharing the same height from point F to the line BD. But what's next? I think we are stuck here, because now we want to know how this triangle BDF connects to this triangle BDC. What's their relationship? We don't know it yet. And the reason is we don't know how point F cuts BC, right? If we know that, then we can say, okay, these two triangles is sharing the same height from point D to BC, right? From point D to BC. And then we can derive a relationship or calculate a ratio. But we still failed here. So we failed in both places. Then what's next? Basically, we don't know how to derive or build the connections between these triangles. Therefore, we have to do something extra, which means that we know two relationships. One is this point. Point E bisects BD. And the other relationship is point D cuts AC in the ratio of 1 to 2. And therefore, we want to convert such relationships to elsewhere. Then how do we do that? And now one theorem comes to my mind. That is, we call that the Intercept Theorem. So that is basically if you have two parallel lines and you have a point from outside and have two lines from that point. Suppose that two lines intersect these two parallel lines at the point A, B, C, D. And let's say this point is P. Then we know that AP to AB equals CP to CD. We call this intercept theorem. Therefore, we can utilize this theorem to transfer the relationship between line segments to somewhere else. For example, let's look at this D. What if we draw a parallel line from D to BC? Right? Now, we can convert this ratio AD to DC to this part. That line segment to this line segment. Right? How useful is that? We don't know yet. We have to take a look. I'm just saying this is one option. Or another way to do this is to draw a parallel line from D to AF. In that scenario, we are converting this ratio AD to DC to this ratio, this line segment to that line segment. And such conversion can help us to do further analysis. Alright, now we'll introduce two approaches to solve this problem, which exactly applies these two methods to draw different parallel lines from point D. Okay, let's get started. I'll clean up the mess here a little bit. Okay. Now, let's call this method 1. In here, we draw DG parallel to BC, and DG intersects AF at G. So let's draw the line so you have a better idea. It's like this. We call this line segment G. Now we find one thing interesting. Triangle EBF, that is the shaded triangle, is similar to triangle EDG. That is because these two lines are parallel, and so the angles, this equals this angle, right? And this angle equals that angle. Good. So these two triangles are similar, and what's more, one pair of their corresponding sides are equal, which is BE equals DE. If we combine these two facts, we have these two triangles EBF is not only similar but congruent to the triangle EDG. We know that EG equals EF. Let's scroll down a little bit. Now don't forget, the whole reason we want to draw this DG is that we want to convert this relationship AD to DC to some line segments on line AF. So we have DG parallel to BC, and this is by the Intercept Theorem. We have AG to GF equals AD to DC, and that is 1 to 2. So this is 1 and this is 2. So if we combine these two facts, okay, let's separate this. If we combine these two facts, we have AG equals GE equals EF. Now we know that the area of triangle BEF equals a half of the area of triangle BEA. How is that? Because their base EF and AE has a ratio of 1 to 2, and they are sharing the same height from point B to line AF. Therefore, we have this. And from here, we have this. We have 1/2 of the area of triangle BEA equals half of the area of triangle ABD. That is because this point E bisects BD. So we use the BE and the BD as their base. And then they are sharing the same height from point A to BD. Therefore, we have this relationship. Good. And from the top, we also have this relationship. Right? So then we know this equals a half times a half times 1/3 of the area of triangle ABC. Therefore, that equals 1/12 of area of ABC. And that equals 1/12 times 360, right? The area of triangle ABC equals 360. Therefore, this equals 30. Then we get the area of our triangle, the shaded part, equals 30. So our answer is B. So that's our method 1. How about method 2? And we'll look at the diagram again. We'll clean up the picture. Good. We want to build the connection of this pair, right? That's our target, which means we want to know where this point F is on the segment BC. And now what we want to do is we want to draw a parallel line DH, which is parallel to AF, and then intersects BC at the point H. Alright, let's write it out. So we want to draw DH parallel to AF, and DH intersects BC at point H. Now we convert this relationship, this 1 to 2, by the Intercept Theorem to here, to 1 to 2. FH to HC equals AD to DC, and that is 1 to 2. So we have FH to HC equals AD to DC, that is 1 to 2. Good. And don't forget, we also have the line BD and BH, which intersects EF and the DH. Then by the Intercept Theorem again, we have BF to FH equals BE to ED. BE to ED. And don't forget, this is 1 to 1, right? That is because E bisects BD. Therefore, this is 1, this is 1. Now, if we combine these two facts, we know that BF to FC equals 1 to 3. Let's look at the diagram again. BF to FC, that is 1 to 1 plus 2, that's 3. Now we can connect DF. If we connect DF, okay, let's put it here. We can connect DF. Then we have this. The area of triangle BEF equals half of the area of triangle BDF, and that is in here. If we look at this picture, we know that we'll use the segments BE and BD as their base, and the height from point F to line BD as their common height. Therefore, we have this relationship. And this quantity combined with this, from these two facts, we have the area of the triangle BEF equals a half of this BDF, right? And that equals a half of 1/4 of triangle BDC. That is because the line segment BF and BD is 1 to 4, and they are sharing the same height from point D to point BC. Therefore, we have this. This equals 1/2 of 2/3 of the area of triangle ABC. This is because this. Let's look at the top. From the top, we have this relationship, right? The area of triangle BDC equals 2/3 of the area of triangle ABC, and it is because they are using the base of AC and DC, and they are sharing the same height from point B to line AC. Therefore, let's simplify this expression. That equals, we cancel this 2 with the 2. So that's 1/12 of the area of triangle ABC. That is 1/12 times 360, which equals 30. We get the same solution 30 as the method 1. So our answer is still B. If you like this video, please give it a like and subscribe the channel. If you have questions, please leave a comment.